graph theory is an important part of decision maths. But graph doesn't mean the same thing in decision maths as you might think. Often when you think of a graph from A-level maths, you're thinking of the plot of a function in a two-dimensional coordinate grid. This graph is not that. This graph is a collection of points and lines that are connected to one another. And the precise location is not actually what matters. What matters is the relationship between the points and the lines. So the points, which are often called vertices or nodes, are connected by lines that we refer to as edges or arcs. And what matters is which vertices are connected to which other vertices via the edges. First little challenge I have for you is, can you construct this shape by tracing over each line once and only once? You can start wherever you like, but you have to try to draw the shape by tracing over each line exactly once. You can't go back over the same line again. You can't use alternative routes to get between the points. Effectively, this is equivalent to the problem of a bin lorry wanting to drive down all 8 streets but not wanting to drive down the same street twice because they've already collected the bins. You want to find the most efficient route. If you've managed to make it happen, see if you can find an alternative route that does the same thing. Is it possible, for instance, to find a route that works starting from any one of these 5 vertices? Another little puzzle for you if you've already finished that. How many times have you walked through the doorway into the room you're currently sitting in? Now, unless you're particularly strange, you probably haven't counted that. But could you tell me whether that number is odd or even? And we might come back to this idea a little bit later. I've also got a little suggestion down in the corner. If you like the idea of puzzles that involve trying to find a route between these different vertices, you might enjoy the game One Line if it's still around. Here's another little puzzle you can try. This one hopefully won't take you too long to solve, but again, you can ask the question, is it possible to make it work starting anywhere? It's been switched around a little bit, so instead of trying to go between points, you're now thinking of moving between rooms. If you look carefully, you'll find this diagram has 5 rooms. There are no external doors. The rule is you start in a particular room, and you can choose any room you like to be your starting room, and then you have to go between the rooms in such a way that you go through every doorway exactly once. Now you've got to properly go through the doorway. You can't just sort of stick a toe in and then back up into the same room and go back some other direction. You have to move through the doorway, transition from one room to the next. Is it possible to find a route that gets you through every doorway exactly once? And once you've solved that one, we can move on to a slightly more famous and more tricky puzzle. The 7 bridges of Königsberg is a famous problem in graph theory, and for many years back in, I think, the 17th century, it was a popular pastime amongst residents of this beautiful city to attempt to find a pub crawl where they traverse every single bridge once and only once. And it would often be the case that you wake up the next morning convinced that you'd successfully completed this particular challenge, but when you went and tried to retrace your steps, you found yourself having to use the same bridge twice, or you realized you've missed off an important bridge that you had to include. Give this a try for yourselves. See if you can find a route through the city. You can start wherever you like. You can finish wherever you like. Let's assume you're allowed to kip on a friend's sofa at the end of the night. You're not allowed to cross the rivers in any other form apart from using a bridge. You can't go halfway along a bridge and pretend you've done it and then sneak back across. You have to stay within the confines of the city, so whatever you can see in this little map on the screen. See if you can find a route that takes you across every bridge exactly once. And when you've had a little play, I will give you some pointers and tell you the sort of thing Leonhard Euler managed to do when he visited the city and applied his impressive mathematical skills to the problem. So the first and most important thing that Euler did when he was presented with this problem was to reduce it to its essentials. Yes, it's a great city and there's all sorts of wonderful pubs on the north bank of the river, but all I care about is that it is the north bank of the river and it's connected by exactly 3 bridges to other places, like the East Island and the West Island, and less directly to the south bank of the river. And all of these places are connected to one another And what matters is that there are essentially 4 different locations that we care about. And then there are these connections, 1, 2, 3, 4, 5, 6, 7 different connections between them, corresponding to the 7 bridges of Königsberg. And then he did one more thing, which was to count the number of routes from each of these places to any other place. And then he asked the question that I asked you a couple of slides ago, which was, how many times have you passed through the doorway into the room you're currently in? And as long as you follow the same rules we've got here about you don't just hover in the doorway and pretend that you've passed through it, then what you should find is you've passed through that doorway an odd number of times. Now, unless you're particularly strange, you probably don't have a number in your head for the exact number of times you've passed through the doorway, but I can be pretty confident that unless you happen to be standing in your own delivery room where you were born, at some point you weren't in this room and you entered it for the very first time. And at that point, the total number of times you've crossed the threshold is 1. And then, presumably at some point, you left the room again. But you're currently in that room, which means you must have returned. So perhaps the total number of times you've passed the threshold is 3, because you start by entering the room and then you leave and then re-enter. Perhaps you do that again, leave and re-enter, leave and re-enter. You can do that as many times as you like, but every time you leave, you must come back. That crucial insight is enough to crack this particular fiendish problem. People have been stuck in it for a long, long time, but Euler came along and spoiled everybody's fun by saying, look, each of these places is a place that if we're going to complete this pub crawl, we have to leave and come back different numbers of times to what would actually work. Let me try to explain what I mean. Imagine you decide you're going to start your pub crawl on the North Bank. Well, then you're going to leave the North Bank by one of the bridges, doesn't matter which. At some point, you're going to have to return by another bridge, and then you'll leave again. So far, so good. So you started on the North Bank, you left it, you returned to it, and then you left it again. Now, that doesn't narrow down any of our options. It just tells us what had to happen. It means if you started on the North Bank, then you definitely don't finish on the North Bank. On the flip side, what if you don't start on the North Bank? Well, then at some point, you're going to arrive on the North Bank, and then you're going to have to leave, and then you'll come back. Which means the North Bank, because it's got an odd number of edges coming off that vertex, it's got an odd number of bridges leading away from it, it has to be either your starting point or your finishing point. If you start there, you don't finish there, and if you finish there, you don't start there. But that same logic applies to the East Island, the West Island, and the South Bank. They're all odd numbered vertices, which means all of them will only work as a terminus, an end point. They'll only work as the very beginning of your route or as the very end of your route, but they won't work as a waypoint in between, because any waypoint needs to be a point that you can arrive at and then leave, and maybe arrive again and then leave again. And if you decide to arrive one more time, you're going to have to leave one more time. Every arrival is paired with a leaving. That's why any country that you've ever visited on a holiday, you have arrived at that country the same number of times you've left that country. Most countries in the world probably have a count of 0 for you. So unless you happen to have visited Mongolia, then the number of times you've crossed the threshold into Mongolia is probably 0. But if you visited, say, Ireland, then maybe the number of times you've crossed the border is twice, because you went there and now you're back in England. Or maybe 4 times, or maybe 6 times. Any point that you don't start at and you don't end at is going to have an even number. Any point that you either start at or end at is going to have an odd number. So the simple solution to this problem is, well, you could blow up a bridge, I suppose. That's one way of doing it. If you delete a bridge, suddenly you've got exactly 2 odd ordered vertices, and you could start at one of them and end at the other one. Look back at the puzzle you had at the very beginning, and you'll see that the only places you could begin, if you're going to draw that shape without taking pen off the paper, is one of the 2 vertices that have an odd number of lines coming off them. So you could start at the 3 here, or you could start at the 5. Pause and have a quick go, and you'll see how much easier it is to solve this problem if you've got this setup instead of having all 7 bridges. Here's one example of a route you could take, and you'll find that it's not actually that tricky to come up with one of your own. Once you've realized what you need to do and you've realized where you need to begin, it's pretty straightforward. Here's an alternative that starts at 5 and eventually ends up at 3. Here's another way of solving the problem. Instead of the destructive approach, what if we decide we're going to build a new bridge? This works quite nicely as well. It works by virtue of changing a couple of those odd numbers into even numbers. You might notice that any time you introduce a new edge like this, what you're actually doing is changing the parity or the oddness or evenness of 2 of the edges at once. So 2 odd numbers turn into 2 even numbers in this case. As long as you start at either the 3 or the 5, this will still work. So I can start at the 3, I can go up, across, around, and there will be a route, in fact many different routes you can find, but all of them will end at the other odd vertex. Okay, the last thing I want to show you is an interesting looking map. I wonder if you can identify it. Now, if you could zoom in close enough, you might be able to see some recognizable names down there in the corner, but in its current form, it's quite likely that you'll be at a bit of a loss. I'm going to add a bit of color for you. Maybe this will help. Do you start to recognize it now? What I love about this picture is that you don't recognize it even if you're somebody who has spent a lot of time in London or loves being on the London Underground for some strange reason. The map we all recognize is going to be this one. And yet this is a map that somehow doesn't have any of the features that we would probably automatically associate with maps. It doesn't tell us where things are because they're not in the right places. It doesn't tell us how far apart things are because the distances are all wrong. And it doesn't even show us what direction things are supposed to be. The river isn't even correct. It's stylized and weird and nonsensical. The only thing this map does is the only thing it's designed to do, the only thing it needs to do, which is tell you the connections between things. So it's done away with directions, with angles, with distances, with relative sizes of things, with relative locations. All it's preserved is the connections between the stations. You can use this map to perfectly well navigate your way through the city, because if you don't care whether you're going north or south, you don't care whether it's going to be a long hop to the next station or a short hop, all you care about is which line do you need to get on next, where do you change, where are you going to after that. This map will do all of that for you. This is the idea behind graph theory. So if you're interested in the process of how you navigate a network like this, how Google Maps figures out the most efficient route for you and how it adapts that when traffic situations change, then decision maths might be the option for you.